A Boeing 777 weighing 350 tons lands at 180 miles per hour and stops in just 8,000 feet. The brakes absorb enough energy to power 500 homes for an hour, yet they don't catch fire. Here's the incredible engineering that makes this possible. When a massive aircraft touches down, it faces one of aviation's most extreme engineering challenges. A fully loaded commercial airliner carries kinetic energy equivalent to a freight train traveling at highway speeds. All of this energy must be safely converted to heat and dissipated within seconds, without system failure. The numbers are staggering. During a typical landing, aircraft brakes convert kinetic energy at rates exceeding 10 megawatts, more power than some small cities consume. Brake temperatures can reach 1,500 degrees Fahrenheit, 815 degrees Celsius, hot enough to melt aluminum. Yet the system must remain completely reliable. Modern aircraft use carbon-carbon composite brake discs that represent a marvel of materials engineering. Unlike steel brakes in cars, these carbon composites actually become more effective as they heat up, maintaining consistent stopping power, even at extreme temperatures. Carbon brake technology borrowed from Formula One racing transforms the physics of deceleration. These discs weigh 40% less than steel equivalents, while handling temperatures that would destroy conventional materials. The carbon matrix structure dissipates heat so efficiently that brake fade. The loss of stopping power due to overheating becomes virtually impossible. Aircraft brake systems incorporate sophisticated thermal management that prevents dangerous overheating. Heat sink design. Brake discs feature complex internal cooling channels that maximize surface area for heat dissipation. The disc geometry creates turbulent airflow that rapidly removes heat from critical components. Thermal barriers. Advanced ceramic coatings protect surrounding aircraft structures from extreme brake temperatures. These materials can withstand temperature gradients of over 1,000 degrees Fahrenheit while maintaining structural integrity. Cooling systems. Some aircraft feature active brake cooling systems that direct airflow across hot brake components during taxi operations, preventing heat buildup before takeoff. Aircraft brake engineering incorporates multiple safety systems that prevent overheating disasters. Anti-skid technology. Sophisticated computer systems prevent wheel lockup that could cause brake overheating and tire failure. These systems monitor wheel speed 100 times per second, modulating brake pressure to maintain optimal deceleration. Auto brake systems. Computer-controlled braking applies consistent pressure that prevents pilot-induced overheating while ensuring maximum stopping efficiency. Brake temperature monitoring. Electronic sensors continuously monitor brake disc temperatures, alerting pilots to potential overheating before dangerous conditions develop. Modern aircraft use multiple methods to reduce brake heating loads. Reverse thrust. Jet engines can redirect thrust forward, providing up to 40% of total stopping power while reducing brake energy requirements. Aerodynamic braking. Deployable spoilers and speed brakes increase drag, converting kinetic energy to heat through air resistance rather than brake friction. Ground effect management. Landing approach engineering minimizes touchdown speeds through optimal glide path design, reducing the energy brakes must dissipate. Carbon-carbon brake technology represents decades of aerospace materials development. Manufacturing process. Carbon fibers are woven into complex three-dimensional structures, then processed at temperatures exceeding 3,000 degrees Fahrenheit to create the final composite material. Thermal properties. Carbon-carbon composites have negative thermal expansion coefficients, meaning they actually contract slightly when heated, maintaining dimensional stability under extreme conditions. Wear characteristics. Unlike metal brakes that wear predictably, carbon brakes develop surface textures that actually improve friction characteristics over time. Aircraft brake systems include multiple safeguards against thermal failure. Fuse plugs. Tire wheels contain temperature-sensitive plugs that deflate tires before dangerous pressure buildup occurs from overheated brakes. Emergency procedures. Pilots receive extensive training in brake overheating scenarios, including taxi procedures that allow natural cooling before departure. Maintenance protocols. Brake temperature monitoring helps maintenance crews schedule brake replacements before wear patterns could cause overheating. Next-generation brake technology continues advancing thermal management. Smart materials, shape memory alloys that automatically adjust brake geometry based on temperature conditions. Regenerative systems, experimental systems that capture brake energy for electrical power generation rather than pure heat dissipation. Predictive maintenance, AI systems that predict brake performance degradation before overheating becomes possible. Aircraft brake engineering demonstrates how advanced materials science, thermal management, and system redundancy solve seemingly impossible challenges. The ability to safely stop a 400-ton aircraft traveling at airliner speeds represents one of aviation's most underappreciated engineering achievements. Every safe landing depends on brake systems that convert enormous kinetic energy into manageable heat while maintaining complete reliability. This engineering ensures that what appears routine to passengers actually represents sophisticated technology operating at the very limits of material science. The next time you feel an aircraft decelerate during landing, remember you're experiencing one of engineering's most impressive thermal management systems, technology that safely handles energy levels that would destroy conventional braking systems.